So welcome everybody to the University of Haifa's Math Department Distinguished Lecture Series. This counts as the 2020 lecture, and if I'm counting correctly, this is actually the 20th lecture in our series, which happens every year. So in 2000 we had Pierre Cartier, 2001 David Kajdan, then Shlomo Sternberg, Joseph Bernstein, Hillel Furstenberg, Peter Sarnak, Yitzhak Katz-Nelson, Matthias Krek, Bela Bolabas, Efim Zalmanov, Vladimir Voivodsky, Alan Weinstein, Peter Teichner, Andrei Semiretti, Yaakov Sinai, Claire Voisin, John Morgan, Barry Simon, Philip Griffiths, and this year we're very happy to have Maxim Kontsevich from the IAGS. His title is Quantum Spectrum in Algebraic Geometry, and David Blank will just say a few words about the speaker. Oh, David, you're muted.
So, welcome everyone. I guess probably many of you know Maxim Kontsevich much better than I. Well, let me just say a few words nevertheless. He did his PhD, I guess it must have been officially at the University of Bonn under Don Zagier, and has worked in a wide spectrum of mathematical fields, so related to mathematical physics, moduli spaces of curves, knot theory with Kontsevich integral, and formal deformation quantization. So in addition to receiving the Fields Medal in 1998, he has won numerous awards, including the Crawford Shaw Prize, Breakthrough Prize, Henri Poincaré Prize, and so on. And as you probably all know, he's at the Institut des Hautes Études Scientifiques, and is also, I see, a professor at the University of Miami. So let's just start the lectures, please, Maxim.
Okay, thank you very much. Yeah, and thank you for the invitation. And I'll start to share my doc. Okay, right. Okay. Yeah, so I will speak about this still very speculative project about quantum spectrum algebraic geometry, which related to some very kind of early years of mirror symmetry and quantum cohomology. And I was asked by Oren to give, I see this audience is very wide, and it's something which I really, for many decades, I think I didn't used to do it, because about quantum homology, I speak to people who know it. And this is something like 20, 25 years ago when I have to give an introduction. But okay, so my first lecture will be really just to recalling what is quantum cohomology, and I'm afraid it will be nothing new for people who know it, but still we should do it. So this plan for today, it's mostly will be crash course on quantum cohomology, and then I'll say about reformulation in terms of Eisenman deformation briefly, and we'll try to give a definition what is quantum spectrum, which we'll discuss in detail tomorrow and day after tomorrow. Okay, so how it started? It was a really absolutely great paper by Edward Witten in '91, two-dimensional gravity and intersection theory in modular space, when he proposes his formalism. And I start to read this paper and figure out an example which Witten himself didn't work out, but from these examples everything started. So it's really kind of really the first calculation, I think, in this subject, which was made. So it will be this kind of archetypical question in Gromp-Witten theory, counting rational curves with some incidence condition, and we do with rational curves in projective plane. Let's say smooth rational curve with self-intersections, like map from P1 to CP2. And if you consider curves of degree d, it depends on 3d minus 1 parameters. Yeah, so let's do simple calculation, because what does it mean, a curve of degree d? You have a map from P1 to P2 of degree d. So in homogeneous coordinates, you get 3 homogeneous polynomial for degree d. Altogether, you get 3d plus 3 coefficients. But then you can rescale all these polynomials. You remove 1, and also you should mod out by PSL2 symmetries of source curve P1. You get 3d minus 1. Yeah, for example, lines which are degree 1 depends on 1 parameter. Quadrics depend on lines depends on 2 parameters. Quadrics depend on 5. And if consider rational curves of degree 3, it will be cuspidal cubics. So it will depend on cubics depend on I think 9 parameters, and cuspidal have 1 degeneracy, 8 parameters. So you get number of parameters 2, 5, 8, and so on. And now to get 0-dimensional space, you should put the same number of conditions. And we say that this count curves which pass through generic 3D minus 1 points. Each point gives 1 constraint, so you should expect some finite number. And it's kind of easy for lines. It's for any 2 points, you have only 1 line. For quadrics, it's a whole pencil. Again, you get only 1 quadric. And for cuspidal cubic, if you consider all cubics, you get 1 parameter family, but discriminant has degree 12, so you get 12 cubics passing through 8 points, and so on. Now, so there's some question. Count how many rational curves pass through of degree d. By the way, if you kind of naively look, you have coefficients of the equation, how many coefficients of the map, and how many equations, and try to see, you get wrong number, because equations are slightly not, you cannot apply Bezout's theorems, it's somewhere at infinity, they're a little bit dependent, so it's really not easy question. Yeah, so the answer that one can calculate all of these numbers. So here are 5 of them, and these come from some recursion. And so I wrote a formula in this recursion, which is a pretty complicated formula. But you see that for each d greater than 2, you can express nd as some expression, some previous numbers. And so if you do it in computer, you can calculate immediately hundreds of them. But also, it's not visible from this formula. It's equivalent of some very ugly differential equations of third order and quadratic in f. F is a generating function when you divide by nk by order of permutation group for this points. Yeah, so you get series with rational coefficients. It satisfies these equations, which is definitely was not human produced. It's a computer algebra make it for me. And this equation actually is related in some, again, complicated way with Penlever 6. Yeah, so let me tell you, before going to the general theory, how one can prove it. One can make kind of proof, not 100% rigorous, kind of Italian style, namely ask the following question. Instead of having curve of degree d passing through 3d minus 1 point, we do the following. We consider curve of degree d on which we have 3d points. And what happens? Maybe 3d minus 2 points will be some kind of mark points on some chosen points on the plane. And 2 points will lie on 2 lines. Yeah, some kind of make complicated equation. So you have some point on a curve mapped to some point on a plane, some point on a curve mapped to lines on the plane. But then you choose also 4 of such points on P1 and also fix a cross ratio. So it will be some intrinsic condition, not condition on incidence, but also condition for some cross ratio of points with parameterization on P1. Yeah, so you get equation depending on cross ratio, and then you degenerate cross ratio to 0 to infinity. Then you try to understand what will be limiting configurations and see that curve degenerates to some previous things and eventually get this equality. Yeah, so it's kind of nice, but very, very bizarre. Yeah, so we have asked a strange question and received a strange answer. Okay. Now, what is kind of real story here? The keyword here is quantum multiplication. So we have smooth projective algebraic varieties over complex numbers. Then we get a cohomology ring over algebra over rational numbers. Just to take H0, which is one-dimensional. I assume my variety is connected, plus H1 and so on, up to the top degree, which is again one-dimensional. Yeah, so we get finite dimensional algebra, which is super commutative, as usual with cohomology, because you have cohomological grading. And it has Poincare duality. So it's graded by integers, and oppositely graded pieces are dual to each other. So let's choose how we can. This is actually not only a ring; it's called what's called Frobenius algebra, because this multiplication is compatible with the pairing, and one can describe this in terms of symmetric tensor. So if you have can consider Poincare pairing as given, how we then describe the multiplication, because it's not degenerate, it's enough to describe the scalar product of two elements with the third element, and we can choose a basis. It's A goes from 1 to dimensional cohomology. And this thing is just integral of a manifold of product of your three cohomology classes, or pairing with this fundamental class. And how one can understand it? Again, so one can take three cohomology classes, then we take external product and get cohomology class on the product of three copies of your variety. And now we pair this class with homology class, which is a fundamental class of the triple diagonal. Okay, and now we see that, yeah, this is completely symmetric description of the usual product. And the quantum product is quantum homology ring is the same Z-graded space. Yeah, so sometimes people say quantum cohomology. It makes no sense because it's the same as usual cohomology. The really new thing is a product. Yeah, and so it's the same vector space, and we completely lose Z grading. We just keep only Z mod 2 grading into the super vector space, and the deformed product I denote by star. I will write, so the goal of my talk of my crash course to give you formula for the star in particular, but it's again with Frobenius algebra with respect to the same Poincare pairing. You don't modify it. So we should this picture should introduce a kind of modified cycle in the cube of a variety. And this idea is that this cycle in the cube of a variety will be cycle of triple of points which lie on the image of some projective line. It could be a constant map, and then for each point in manifold there is only one map from projective line with 3 points, because to this point, because there's only one rational curve with 3 points. But then it could be something else. Just anticipating the kind of first interesting example, I would say that if X is a projective space, then this quantum product is given by cycle which consists of two components: the fundamental class of the diagonal and the fundamental class of triple of points which lie on a line, kind of collinear points, and it will be this quantum product. Yeah, that's a rough idea, and one should do something more rigorous about it. So the whole story, kind of after reading and interpreting Witten paper, we wrote a paper with Yuri Manin, with kind of axiomatic approach before actual construction. Then construction was made later. And we call these things Gromov-Witten invariants because not only we are reading, of course, Witten paper, but there was kind of key idea of Mikhail Gromov related to different subject, to symplectic geometry, and the whole thing kind of lives between two chairs. It's partly algebraic geometry, it's partly symplectic geometry. But let's do it, speak about algebraic geometric framework. So I will speak about only genus 0 part, because higher genus it's not really yet understood. At least algebraic, what is algebraically goes on, it's no complete understanding. But genus 0 it's really the central part of the story. So the input is a smooth projective algebraic variety. And in fact, one doesn't really need to specify concrete algebraic variety. You consider have to specify variety up to deformation, continuous deformation. And the same in symplectic world. You don't specify concrete symplectic manifold, but you can change symplectic structure to get the same result. Yeah, so the input is really discrete data. There's no continuous parameters here. And the output is the following. For any non-negative integer n, for any d, which was before number, but now it's homology class, it will be future degree of my curve. And for any n homology classes in my variety with rational coefficients, I'll take have the correlator, which I denote the in brackets is product of this observables, whatever it means, and with indices 0 and d, 0 indicate genus. I will later omit it because I'll do only genus 0 and degree d. And now I'll give you the formula for which I'll explain various pieces. Now, so the result will be a rational number. So it will be polylinear functional on cohomology, depending on this degree of a curve. Now, what I do, I integrate over certain homology class somewhere. Namely, it's called virtual fundamental class, and it's of certain modular space, which I'll explain in a moment. This modular space map in many ways to your variety. Evaluation maps, it's like parameterized rational curves, and to take pullback of your classes, take exterior product, and integrate over this virtual fundamental class. So what is this? Oh, sorry, I forgot to put really important. I think it should be M0n bar. It's not this. I will submit kind of corrected notes after. So it's actually M0n bar. It's a modular space. It's x and degree d. It's a modular space. In fact, it's not a space called stack, because objects have some symmetries of something which I kind of guess from Witten's paper, but it wasn't written there. Stable maps, which are what is a stable map? In my first example, I consider just actual map from genus 0 curves. But in the procedure, I have to consider kind of degeneration. So I consider some kind of degenerate curves. And the degenerate curves which I consider will be curves with only nodal singularities. It will be trees of rational curves. So it will be connected curves with nodal singularities as arithmetic genus 0. And with marked points, which will be pairwise distinct and not nodal. Now, so I consider such maps. And the stable means that this object has only finitely many orthomorphisms with no continuous parameters. So this curve, bunch of points in the map to given x has essentially finite many orthomorphisms, which can be translated to some geometric condition, namely the following. If you consider any component of your nodal curve, irreducible component which maps to a point, then on this component, if you remove all singularities and all nodal points and mark points, you should get negative Euler characteristics. So because it's CP1, you should remove at least 3 points. Yeah, this reminds the definition. Yeah, it actually was generalization of stable curves by Delaney-Mumford. If you X is a point, then everything maps to a point. Then the condition will say that each component will have at least 3 special points in this case. And you get a very nice, smooth, compact orbifold. Not a manifold, because these objects still have finite automorphisms and locally divide by them. So that's the space of stable maps. And let me just draw the picture, how one can look on it. Yeah, so in fact, because the science belongs to 2 communities, to symplectic topology and algebraic geometry, there are kind of 2 pictures which you do. Symplectic topologists would like to think about pseudo-holomorphic maps with the same stability conditions. And then you map actual spheres, union of spheres, get trio spheres, and there are some arc point, which is kind of like thick dots here. And as a condition, for example, in this example, you see that there are 2 dangerous components when you have only 2 or 1 special point, just one on the left, one on the right, and they cannot contract to a point on X. Otherwise, if you contract, then you get the group of orthomorphisms will be not finite. You have like C star, for example, always contains in this group. Yeah, so that should be actual maps to actual curve, but all the 3 others can contract to a point. Yeah, algebraic geometry will, if kind of he works over any field, and algebraic geometrist will draw a curve as a line for himself, and then it will be a diagram. So instead of spheres, you get just lines, and you just put here points. And there's also kind of convenient way to draw to represent such things as a dual graph. So the vertices of the graph will be irreducible components of your curve. Edges will be nodes when 2 components intersect, and dashed lines will be mark points. So it's all equivalent languages. Okay, so now I would have to say something about the virtual fundamental class. Now that's technically it's the only thing we should do. The rest will follow. And when we wrote with Mani our paper, there's no yet theory, so it was our paper was completely formal, but maybe in some simple examples like projective spaces, our calculations can be justified because the space has accidentally right dimension. Yeah, yeah. So that's the whole story. When it started, kind of. The prediction should be some nice theory of virtual fundamental class. There are many attempts. Actually, I myself will propose some definition, maybe in 93, 94, using homological case theory. But for many years, what was kind of golden standard in algebraic geometry was work by Kai Berendt and Barbara Fantecchi, which honestly I didn't really like the approach, but it's kind of worked. And it was for many years, and then there were some better ways to formulate it. It was work by Dominic Joyce and so on. And but it's I think still continued. And maybe 2 years ago, Adel Khan came to a very nice and kind of clean, really definition from the book. One can say it cannot make it simpler in terms of derived algebraic geometry. Yeah, so finally, I think we have really satisfactory definition. It took many years eventually to clean this subject. Yeah, honestly speaking, I think it's maybe can be made still better, but it's at least it's completely short and clean definition. Actually, there was a parallel development in symplectic geometry. I didn't mention names. I think it was first maybe Rohan and Tian construct this fundamental class. And then there were various other groups making constructions. Then there was a story about graph-fit invariance with boundary, like open-closed invariance, where there was a lot of controversies, and some people didn't believe other people, and so on. And yeah, but at least for this closed cases approach, Adel Khan also works, I think, equally well, at least for closed case in real symplectic geometry as well. Okay, so what? Yeah, so there is a good formalism, yeah, but now we have to apply it. So the story about virtual fundamental class, it's not about modular space of stable maps, but there are few hours, maybe about 5-6 other problems of the same type in low dimensional algebraic geometry. But to get integration, first things you need is compactness. And this modular space is compact. It's actually analog of result by Gromov in symplectic geometry. That's the first property. But now, in order to really to have virtual fundamental class, one needs what's called perfect obstruction theory. So what does it mean in plain terms? So locally, your space, it's I remind it's not only space, it's kind of stack. You locally divide by finite, it's maybe Deligne-Mumford stack. You divide locally by finite group. It looks like this. Suppose you have some complex manifold algebraic or whatever, Z of certain dimension. Here I got two submanifolds, also without singularities, and you intersect them. Intersection could be not transversal, and that will be your space, but after maybe finite covering. So imagine, more precisely, imagine that we have such situation, a manifold and two submanifold, which is invariant transaction of some finite group. So you can make intersection and take a quotient by the group in a sticky sense. Yeah, so this representation, it's not unique, but there is something, will be some class of such representations, form some filtered system, and the property is the following. So these varieties, y1, y2, and z have some dimension which I didn't specify, but if you make this alternating sum of dimension y1, y2, and minus dimension of z, so it is expected dimension if they intersect transversally, then it will be something given for you a priori. And in this case of stable maps, it's this number, dimension of x minus 3 plus integral first Chern class of my homology class plus number of mark points. Yeah, this what is the meaning of this number? Yeah, one can again in relation with the story, one had to think about general deformation theory of everything, like the stable maps, and there was old formalism by Illuzy, tangent complexes. Yeah, these days one should do maybe derived algebraic geometry. And what is nice for this question for maps from nodal curves, this tangent space to the space of maps when try to deform, it turns out to be zero cohomology of certain complex concentration degrees 0 and 1. It's like sections of vector bundle on a curve. Because curve is one dimension, don't have high cohomology. And then you can calculate its earlier characteristic, and this is earlier characteristic. So if you are lucky and the intersection is transversal, then it is right dimension. But in general, when you get this structure, you see the dimension of kind of schematic dimension of this intersection is always bounded below by this number. And the virtual fundamental class, the meaning of virtual fundamental class, it's informally you move a little bit your subvarieties, so they intersect transversally. The intersection will be situated in the very close to the original intersection, so in the tubular neighborhood, and kind of you moved back homotopically and get to this class. Yeah, so one can do it in more abstract cohomology theories, like algebraic cycles, Chur groups, and so on. Yeah, so that's a fundamental class, and this virtual fundamental class will be homology class or element of Chur group exactly of this expected dimension. And in real sense, it will be twice the dimension because it's dimensional complex numbers. Okay, so that's a main technical tool. There's nothing. The rest is complete formality. But to apply this formality, one should kind of have certain bunch of properties which we axiomatize with Manin at that time. And here's this, I think, the full list of axioms. So this, most axioms are completely obvious, but let me just discuss all of them. First of all, this polylinear functional is symmetric in the graded sense, or if you permit to use causal rule of signs, it's just as you do with cohomology classes or forms. It's completely obvious. The second thing that this thing is if it's non-zero, what can happen? Can happen two things. Either your curve maps literally to a point, then this homology class will be zero, or it should have mapped to actual curve or union of actual curves, and then it should have strictly positive, let's say, volume with respect to Keller class. And it's delicate but essential difference because, for example, second homology can contain a torsion. And this class's image of D, so the second homology group will be some lattice plus some torsion group. And what the support property said that if kind of lattice part is non-zero, lattice part is zero, then the torsion part is also zero. You cannot have a map with whose class is non-zero but torsion element in H2. Okay. So the third axiom said that what happens with constant maps? With constant maps, if one remembers the definition, what is a stable map? Yeah, at least if your curve has just only one component, then it should have at least 3 marked points. Otherwise, it's the same for more degenerate curves because otherwise it will have symmetries. So the number of marked points should be at least 3. And if it's 3 marked points, then this space of stable maps, it's exactly will be space of set of points of your manifold, and this thing will be integral of product of your 3 cohomology classes. If the number of points is more than 3, then the thing is 0. Like imagine you have P1 with 4 points mapping to a point of your X, and it has a cross ratio. If you change cross ratio, you do nothing with your evaluation map, so you get kind of dimension in your modular space on which nothing to integrate, so you get 0. Yeah, so it's for degree 0, you get only n equals 3 and usual kind of classical product in pairs with Poincare duality. So this third thing, it's dimension axioms. We said that it thinks non-zero if and only if the degree of cohomology classes which you integrate is exactly coincide with degree of your homology class, which is expected dimension. Now n will be not a number of points, will be dimension of your manifold. Then the third next axiom is unit axiom. Namely, if one of your field is identity, unit and H0 of your second zero homology of your manifold, and if you consider non-zero degree map, you get nothing, because what happens, you have kind of like free point moving along your curve, and you integrate nothing over it, so you get 0. For degree 0, it's not the case. Yeah, so you get, for degree 0, you get product of 1 and Poincare pairing. Yeah, yeah. So it's kind of really little details, but they kind of fits very well to some abstract structure at the end of the day. So the next axiom is still elementary axiom, is divisor axiom. If you have, if you integrate, maybe d is not equal to 0 here. If you integrate the product of several observables over model space of stable curves, and one of observables is to form, close to form, then you can remove this running point from the integral, because you can kind of see that have running point, and you integrate to form, you get some constant, and you reduce to integral of a smaller number of points. Yeah, all the axioms are essential but pretty trivial, and the main thing it's WDVV. It's Witten digraph Verlinde equation. Yeah, that's really the most essential part of the whole thing. Namely, you have many elements of your cohomology ring, at least 4. So it will be first, second, third, fourth, and maybe fifth, and so on. But first 4 will be essential for me. Now, it's if you remember when I told you about this original argument about counting of rational curves over in P2, the argument was kind of ugly. I should consider something, some special condition in some choose 4 points, some cross ratio. This is exactly this 4 observables. Yeah, so the property is completely universal. So it's here there's no distinction between 0 and non-zero degrees. So I fix this many classes, fix any degree d, and then I get the following huge sum. I decompose my degree in sum of 2 smaller degrees. I decompose my set of quantum cohomology classes starting from fifths to the whatever they are into 2 disjoint groups, I prime and double prime. And now I do the following. I consider correlate product of 2 this Gromp-Witten invariants. I consider count maps of degree d prime, and with observables phi1, phi2, phi of first group, I prime, and some other homology class delta j, just choose some basis, and then I do the same with phi3, phi4, and sorry, there's some kind of misprints here. It's phi I double prime, and I take dual basis, so ij delta j and delta upper j form a Q-net decomposition of the diagonal. So I make this huge sum, and then it's symmetric if I interchange, say, phi2 and phi3. It's completely symmetric in these first 4 fields. So what is the pictorial explanation here? I imagined I map stable maps where my curve it's kind of explicitly split in 2 groups, and so it's a union of 2 curves, which again could be generally not reducible, but let's imagine for simplicity they are reducible. So I get one picture, another picture, and this is exactly the limit in a Deligne-Mumford moduli space of cross ratio goes. Consider model space of 4 points on P1. It's one-dimensional model space. It's CP1 again on curve of genus 0. And when I go to the limit, cross ratio goes to 0 to infinity. You get exactly these 2 degenerations. Yeah, so that's independence of cross ratio. It's a kind of 4 points is a key argument here, which implies this WDVV equation. Yeah, that's I think the whole collection of structures we know in general. We don't expect anything more. And all these trivial and not so trivial axioms play the role. So what one can do with this? First, we make a generating series. It's called Gromov-Witten potential, and in genus 0, because I do it in only genus 0 curves. Why I don't speak about high genus curves? One can do something, but there's no notion of cross ratio, so this WDVV equations completely disappears in high genus. Yeah, so it's it will be much weaker structure. So I make this geometric series. So I take sum of all possible correlatives which I have. So I choose a basis in my cohomology space. Also choose an ample class just to keep track of degrees of a curve. One can do it some smarter way, some monoid rings and so on. It doesn't matter. So I consider correlators, all possible correlators of arbitrary number of elements of my basis, multiply by some variables, just to keep track. And variables will be super variables. It will be odd and even variables. Parity depends on parity of the degree. And divide by n factorial because this thing is symmetric. Okay, so I get huge series. It's series in finitely many variables, namely corresponding to the basis of cohomology and this extra variable corresponding to counting with respect to ample class. One can be again, one can be a bit more serious. Could be not one variable capital T, but rank of neuron severity group. So how many kind of independent directions in second cohomology. Okay, they get series in finitely many variables. And now I define a quantum product on cohomology, which depends on all these parameters. One can extend by linearity to program cohomology with coefficient in this ring. The product of two base elements, it's given by third derivative and multiplied by dual basis element. And WDVV equations means exactly this product is associative. It's commutative on the nose, and it's unital on the nose by previous axiom. So I get family of commutative associative product on cohomology. These are quantum products which I promised to talk from the very beginning. Yeah, but instead of quantum products, I would like to say better say that it's better should interpret it as in some geometric way. The story is the following. There is maybe I return to axiomatics. There was a dimension axiom, yeah. As a dimension, you get something about first chain class, blah blah blah, and degrees, and this also should be taken into account. It's some certain kind of affine homogeneity of geometric series, and because of homogeneity, it turns out it's very convenient to add extra coordinate to this all parameters. And this coordinate I denote by u. This is u even variable. And what I'll construct, I construct a trivialized bundle with fiber cohomology of my manifold. It will be super vector bundle, and the base will be super manifold, formal super manifold. It will be not totally formal because it will be formal power series in my variables ti and capital T, but actual polynomials in U. One can make a little bit more. One can also see that because of unit axiom, this thing is not a formal power series, but actual like polynomials in variable T corresponding to identity in H0. But one can gain extra non-formal direction, but that's the only one thing one can do. Okay, so I get some super base, which is a product of something and this U plane. And I'll construct a flat connection. Actually, it will be meromorphic connection. First, I'll write connection in all directions. So there are three types of coordinates. The connection and this connection depends on kind of three matrices. So there is some matrix K. This is some operator K acting on cohomology and depending on only on parameters small t and capital T, which is the following. I consider first chain class of my tangent bundle, And then, so it's element in second cohomology, and add some little correction to it, which is the following. I take some of all my base elements of degree not equal to 2 of the following things. Degree minus 2 over 2 multiplied by ti times delta I gets an cohomology class linear depending on small t, and consider quantum product which depends somehow on this small t and capital T. Now, of course, I said that it's you remove from summation class of cohomology degree 2, they are present but with weight 0, as you see. Yeah? So in degree 0, you see, in degree 2, you see only first cohomology, first chain class of tangent bundle. Yeah, so basically, if you, for example, if you vary only by even classes, you add classes of degree 4, 6, and so on. You also add class in H0, but it's so stupid by identity element, it's really nothing to talk about. Yeah, so it's roughly, you correct the classes of degree 4 more. Yeah, so I get this matrix valued function on this small t and capital T. Then we have operator G. G is something which doesn't depend on anything. It's grading operator in cohomology, but graded in, but kind of normalized in some funny way. So at first it's kind of centered. In the middle cohomology get 0, and so you remove complex dimension. So you get this grading will be symmetric with respect to 0, and then also divide by 2. And finally, you get operators AI, which will be quantum products with base elements, again, depending on small t and capital T. Oh, by the way, I want to say that one can remove from the gain the small t, which correspond to class omega. You don't lose any information. Okay, so now what is the formula for this connection? I get connection along u variable is because trivial bundle would just consider this horizontal vector field plus 1 form, or apply to du. So it will 1 u squared times k plus 1 over u times g. So what's interesting, you get connection with apparently irregular singularity. Maybe regular to infinity, but irregular at 0. And it has only 2 terms in Laurent expansion, -2 and -1. Along ti, you get du ti plus 1 as u times ai. And for this capital T, it's get u1 times a with index correspond your base element you can choose, which correspond to ample class omega. So you see that from this picture, you see that you can remove this variable ti2 from the game completely because it's nothing to do to the game. Okay, so that's so I get connection in many variables, but the right point of view, I would suggest it's to see it's the u variables. It's a main variable. You get the special class of connections, which we'll discuss in detail next time. And the extra this ti and capital T will be extra parameters for which you get kind of isomonodromy deformation of this connection. So that's actually explained why in this original example from P2 you eventually get a relation with Penn-Levy 6, because at the end of the day it's again isomonodromy equation for some connections. Okay. So this series F0 and many variables conjecturally converge near 0. I have absolutely no doubts that's true, but up to now nobody was able to prove it in complete generality. Yeah, so it's maybe it's not so difficult. At least in algebraic geometry, in symplectic geometry, it's probably more tricky. But up to now, nobody really was brave enough to attack it. Although all examples and all evidence shows that it's the case. Now, so one can assume it or can live with it without it, but okay. So now, first, it's maybe the time to start with first and maybe the last example for today's talk. It's a complex projective space of arbitrary dimension, capital N, and my ample class will be first chain class of line bundle of 1, the simplest possible ample line bundle. Yeah, so the cohomology, the usual cohomology of my variety is a ring generated by class omega, and it's truncated polynomials. So this class raised to power n plus 1 is equal to 0. It has obvious bases, 1, omega, omega square, and so on. And multiplication by omega is obviously nilpotent lower diagonal matrix. And cohomology ring is also nilpotent. If kind of maximal ideal is important. It's local ring. And now let's consider quantum cohomology. And here one can convergence issues are empty here. One can put the small variables t equal to 0 and actually not empty, at least t equal to 0, but one can put capital T equal to 1 and small t equal to 0. Just naively count all curves without putting any observables. And then the ring will be semi-simple in this case. What will be multiplication by omega? I claim what you add, you get just extra 1 to this nilpotent matrix and get matrix of cyclic permutations, of the cyclic permutation. So the, what really goes on? So we consider triple of points which stay on some rational curve of degree 0, 1, 2, and so on. Degree 0 gives me triple of coinciding points. You get triple diagonal. In degree 1, you get triple of collinear points. But if you count what goes on from curve of lying on a quadric, you get 0 cohomology class. The reason is if you have like 3 points on projective space, you can imagine some the lines in some plane, say, and this plane, it's only 3 points, not 5 points. There are many quadrics passing through it. So you get modulus space of quadrics, which projects by evaluation to triple points, has fibers of positive dimension. So you definitely get 0 homology class. Also, by dimension reason, get class something of which doesn't have really no room. The degree, virtual dimensions beyond what is possible in this Q-process variety. Yeah, it's the same for cubic curves and so on. So you get just 2 possibilities, curves of degree 0 and 1. And if you count from this one and make this multiplication, you get exactly this extra correction, and you get the ring. It will be a ring of functions on roots of 1, just semi-simple ring. And matrices K and G in this case will be pretty simple, because canonical class is n plus 1 times O1, it's O n plus 1. So we multiply this quantum multiplication by n plus 1. You get roots of n plus 1 multiplied by n plus 1, which will be eigenvalues of K. And G with this grading matrix, which is made kind of symmetric with respect to 0. So the definition of this quantum spectrum of my variety, which depends on this point in at least the domain of convergence, is the spectrum of this operator K. It's not the spectrum of the ring, I prefer, which could be larger, but just the spectrum of this operator. And if you assume convergence, we consider a finite subset of complex numbers. Without convergence, one can maybe put small t also depending on capital T. It will get subset of algebraic closure of field of Laurent series in one variable. Yeah, so there are kind of 3 basic classes of varieties, depending on a sign of the canonical class. It could be ample class, anti-canonical class. Then it's called Fano varieties, something called projective space, when degree of variety is much smaller than the number of variables. And usually in this situation, this spectrum is big. It's definitely more than 1 point. If it's Calabi-Yau variety, when first Chern class is equal to 0, or it's of general class when it's strictly negative, then the spectrum is always 1 point. It follows from the calculation of dimension. And you see that this quantum product, this will be kind of preserves the degree by decreasing filtration by cohomological degree. So it will be automatically nilpotent operator. Yeah, so good. sometimes interesting, sometimes not interesting story. And in general, we get countably many interesting series F0, or quantum many these quantum products or connections, because it's all depends on the deformation theory. And somehow it's expected this related to some kind of algebraic geometric object, mirror object. Although for this we don't have really total evidence. The most common case it's some kind of Landau-Gisworth model, get some variety, maybe a non-compact one. Dimension could be larger than dimension of your variety by some even number. The canonical class of this variety will be trivial. So the non-compact Calabi-Yau, and you get function such that critical set of critical points is compact. Okay, and for fun, when you get varieties of volume element and function, try to write exponential integrals, like projective space, you write exponential integral like this. For Calabi-Yau varieties, you don't do exponential integrals, you just see that this geometric series comes from variation of Hautes structure of some mirror manifold if it exists, or maybe some variation of Hautes structure. For general type, this function is in general not interesting. It's kind of polynomial, but very often it's really nothing except constant map. So you get only the classical limit. You get just usual product on cohomology and get cubic polynomial. So as I told you, the theory of Gromov-Witten invariance doesn't depend on continuous deformation, and by Gromov ideas, it can be defined for any compact C-infinity symplectic manifold. So one can ask, is it part of symplectic topology? I would say no, because one can define this potential even for varieties of a finite field. There's no symplectic manifolds, no Foucault categories, yeah, but still there's these functions, and it's completely unexplored story. For example, if there are varieties you cannot leave to positive characteristic, what will be this Gromov-Witten invariance? We have absolutely no idea at the moment. And so this story belongs kind of to two worlds, and algebraic geometry and symplectic geometry. And I'll talk about non-trivial interaction between the two viewpoints. Just even the basic fact that this fundamental class is algebraic, it has really important consequences. So now I'll just say what will be the goal of my lectures. I want to explain this Gromov-Witten theory. When considered as a sub-subject of algebraic geometry, it's not just a collection of some bizarre answers to bizarre questions, how many curves, and get this complicated version of Penlevi equations, which could be safely ignored if you do something else like birational geometry, motifs, blah, blah. Yeah, what I want to say is that it's really center part of algebraic geometry, and should be really much more popular. And like people from all generations, some people didn't really follow on it and are happy live without this, but I not think it will be possible in the future. So this thing goes to the core of other topics, and I will mention this will be my talks, will be something related to semi-orthogonal decomposition, which was developed for many years in Moscow School by Bondel, Kapranov, and Kuznetsov. Also, it's related to give some new interesting result for motivic integration, cut and paste invariance. Also, hypothetically, it's all pretty hypothetical right now. It gives a really very new invariance in birational geometry, and gives new viewpoint on many more problems, and possibly gives categorification of intersection homology. Okay, thank you.
Okay, thank you.
Okay, so I finished just in time, suppose, yeah. Yeah.
Okay, I'll open the floor to questions.
I have a question about non-compact story. Physicists speak about a model for non-compact, at least Calabi-Yau. So is it a part of the science? Are there axioms?
No, the story is the following. For non-compact varieties, one can put certain condition, namely conditions the following. If you fix a point on your variety and fix a degree class in second homology, degree of curve, and consider all curves passing through your points for given homology class, they stay in a compact part of your variety. So it's some kind of class of variety convex at infinity. For example, it could be a fibration of a fine base with projective fiber. or there are more examples. So I get some class of examples when the story is defined. There's no Poincare pairing, but there is this connection and so on. This flat connection. As far as I know, there's no explanation for Foucault categories, but you get at least this isomonormal deformation as well.
So the question about the spectrum, does it have meaning?
Yes, spectrum. Yes, definitely. One can speak about spectrum and so on. Yeah, but I didn't thought much about it. But it's definitely works for some class of non-compact varieties.
Okay, thank you.
Can I ask, please? So can you say again about the motivation for introducing this extra variable u?
The reason is to keep track of grading axiom, dimension axiom, when you get first chain class and something. It was certain homogeneity one can encode. This, yeah. At the end of the day, this structure, this isomonormal deformation, as we understand now, appears in very general contexts. Some kind of deformation of triangulated categories, and U is a universal variable one can do in kind of like calculus for periodic cyclic homology. Yeah, so it has some its own meaning, but here it introduces purely formulae. For example, this has some explanation hypothetically when you have Foucault categories, but when you get varieties of finite fields, there's no Foucault categories, and these things still exist.
Sorry, so what is the explanation in Foucault categories?
Then you have Foucault categories, Foucault category for your variety, and then Foucault category, it's a Calabi-Yau category with something, and this automatically gives such isomonodromy deformation.
And so you mentioned that in this abstract setting for periodic cyclic homology, it has some other meaning.
Yes. No, in general, if you have, let's say, A-infinity algebra, you get on homological Hochschild complex, you have differential and con-differential. And then consider linear combination with consider usual differential plus U times con-differential, and consider homology, get cyclic homology. So this constant which you add, you consider linear combination. I denote by U, some other people don't by other letters, but it's really universal. It's kind of generator of homology of CPU infinity, kind of universal first chain class.
Thank you.
Any other questions? Okay, well, let's thank the speaker again. And we're going to resume tomorrow at the same time. And Maxim, if you have notes from today, could you send them to me?
Yeah, I have to correct a little bit. I noticed several misprints. Yeah, but yeah.
Okay, so any notes or videos will be eventually posted to this website, which I'm posting in the chat. And I'll see everybody tomorrow. Thank you very much.
Okay, thank you.